Good morning. In the yesterday's class, we discussed regarding one application of discrete logarithm, that is Diffie-Hellman key exchange. Today, we are going to discuss the second application, that is Gamal encryption. So, Gamal encryption is also based on discrete logarithm. In Gamal encryption, we select a large prime number p, like that of in a Diffie-Hellman key exchange, and a generator G, so which belongs to set ZP. So P is large prime number, G is a generator of that set ZP, and in Gamal encryption we talk of selecting a private key A whose range is between P minus 1 and 1. Then he will publish a public key corresponding to a will be P G alpha, which is a triplet. This triplet will going to act as a public key of a party A. The small a is some number which will be a private key of A, and the triplet, that is prime number and a generator of the set and a alpha, will these three will act as a public key. Now, how to obtain the alpha? Alpha is what we call it as an encryption key. This is obtained by using this formula. Alpha is equal to G raised to A mod P. Then whenever a party B wants to send something to A, the secret message, A will going to encrypt the message using the public key of A, that is this triplet. Using this triplet, it will perform the encryption of a message that is supposed to be sent to A. So to perform this encryption operation using the public key, what B will do, we'll see. The job of a B first is to select some random number, we call it as R. So this range of this R is between P minus 1 and 1, and the R is so selected that R must be relatively prime with P minus 1. So that is the GCD of R comma P minus 1 must be 1. Now B will perform this calculation. First he calculates a C1. Okay, C1 is equal to G raised to R mod P, where R is some random number. G raised to R mod P already has these two values, G and P, and similarly he also calculates C2 using the encryption key alpha, that is m into alpha raised to R mod P. So then he sends both C1 and C2 to a party A. Now when it comes to the decryption of a message, what A will do is A has to use its private key. What is the private key of A? It is small a. Small a is the private key of A. So what party A will do is, after receiving C1 and C2, okay, A will going to compute C1 raised to minus A, comma, bracket, into C2 mod P. He will perform this calculation at receiving side. A will perform this calculation. So by doing so, A will going to get the message. Now we will mathematically prove that how A will going to get that. So as I said, that decryption operation involves a private key, that is C1 raised to minus A into C2, we said that C2 mod P, fine, mod P will helps us to get the message. So I have written it as it is, C1 raised to minus A into C2 mod P. Okay. So what is C1? According to us, the C1 is, so what calculation we did at a receiving side, those values we will going to substitute over here. That is C1 is equal to G raised to R mod p raised to minus a. Then m, that is message, as it is. Now I will going to substitute for C2. This is what is the substitution for C2, alpha raised to r mod p bracket complete. Now already we know the properties of these multiplication properties what we have discussed in the first module. Using those things I will rearrange the terms. Okay. After rearranging it, this becomes g raised to minus a into r into g raised to ar, because alpha's calculation you know, so that value I substituted over here into m mod p. This is because alpha is equal to g raised to a mod p. I hope you understood. So g raised to ar mod p is mainly because of this reason. I have replaced this alpha by this value. Okay. After doing this, after rearranging these terms, this term minus ar to ar becomes what? It is 1. So if it is 1, then what will be left out is m mod p. So p is less than m is less than p. So we are getting m. So this is how we are obtaining a message by using a private key. One more thing regarding this Gamal, that the ciphertext, that is C1 comma C2, whatever we have generated before sending it to A, its size is twice that of the message. Okay. So twice the size of a message. So this is what is a speciality of Gamal. Now we will discuss one simple example on Gamal. Let p is equal to, p is a prime number, that is equal to 1 3 1, and g is equal to 2, and we will stock of a is equal to 97, and these are the parameters which are given to you, and we are asking you to find say C1 and C2, and we will also ask you to decrypt the message. Okay. So we will perform that operation. First we need to find out alpha in this whole process. Alpha is equal to 2 raised to, that is a, 2 is generator of the set. So g raised to a means g raised to 97 mod 131. Okay. So I use this formula. Is it clear? Next, once we get a alpha, okay, now we will talk regarding message that is supposed to be sent. That I will take message is equal to 75. Assume that message is 75. We are supposed to encrypt it and decrypt it. So encryption is happening at sending side, decryption will going to happen at receiving side, and we should prove that mathematically we are going to get a 75. Okay. So what exactly a sender will do, we will see. You know that the first step in the sending process is selection of some random number r. So here we will take r is equal to 33, which must be relatively prime with p minus 1. P minus 1 is 130. So it must be relatively prime with this. Selection of r should be such that it should be relatively prime with this. So anyway, we know that it is a even number. Yes. So make sure that we should go for some odd number. It is not always true, but what I am saying is that is a way what we can do. Otherwise, you just use Euclidean algorithm to find the prime numbers, whether they are relatively prime or not. Okay, so select R such a way that it should be relatively prime with 130. Next, we need to calculate the C1. So this is what is the procedure that happens at a B side. C1 is equal to G raised to say R mod P. What is G? G is 2. It is 33 mod 131. So after computing this value, I calculated, so it comes somewhere around 103. It is 103. And then we need to find out C2. C2 is equal to, as you know, that m into alpha raised to r mod p. I'll substitute the values. M is equal to 75 into r is alpha is alpha. We have not I have not written the value that is obtained by performing this operation. It is somewhere around 14. Y is equal to 14 raised to 33 mod p. After expanding and performing mod operation, we are going to be land up with the value 51. So my C1 is 103, my C2 is 51. The message that is supposed to be sent by B to a is C1 comma C2. You know that what is C1? C1 is 103, C2 is 51. This is what is the thing that is sent by B to a. So once A gets this message, A has to decrypt the message. It has to use its private key. What is the private key of A? In the problem it was stated it is A is equal to 97. So now A has to decrypt the above message. The procedure is C1 raised to minus A into C2 mod P. Okay, we'll substitute the values. C1 is 103 raised to minus 97 into 51. C2 is 51 mod 131. I hope it's clear. So I just substituted the values of C1 and C2 for decryption purpose. We know that this is my A's private key. Using private key, the A will going to decrypt it. So this is what is the procedure of decryption. I hope it is clear. So next, once it applies, it will going to be say 103 minus 97, then multiplying this and performing a mod operation altogether. In the end, we will going to get say 75. Actually, we need to find say minus 97, 130 minus 97, it comes somewhere around 33. So actually it is 103 raised to 33 mod 131 and into 51 mod 131. Together, if you perform multiplication and if you perform 131, you are going to get a 75. This is how you need to calculate. Thus A recovers the original message using her private key. Entire strength of this Gamal again is dependent on the value of P. For example, knowing C1, G and P, it is computationally infeasible to find R. If not, an attacker would be able to deduce m by using computing alpha raised to r mod p, then computing c1 c2, then he may compute c2 into alpha raised to r whole raised to minus 1 inverse of that mod p. When it comes to Gamal, the precautions what all we need to take is, the one important precaution is that whenever we are using a random number, the same random number should not be used again. In case if you reuse this random number r for two different messages, then there is a possibility that hacker may get the message. We'll consider a situation where hacker knows he has an access to a ciphertexts that are created by two messages. One is m1, another is m2, which are encrypted by using a same random number r. Okay, so we'll say that the ciphertext that is created out of m1 is c1 comma c2 is equal to g raised to r mod p comma m into alpha raised to r mod p. Yes, and ciphertext because of m2 is c1 dash comma c2 dash is equal to, again generator will going to remain same, that is g raised to r mod p and m2 into, this is m1, to alpha raised to r mod p. So we'll assume something over here. Say the hacker knows that he by dropping he comes to know regarding, say, both pair of ciphertexts, that is he knows this as well as this. And in addition to this, if we'll assume that hacker also knows the message m1, I mean to say message m1, then he may obtain the value of second plain text m2 as follows. Okay, with these assumptions, okay, the obtaining of m2 with these assumptions, hacker has an access to these two things. By dropping he has taken out these values, and then we'll assume that he also knows m1, because like say m1 has encrypted long back, and we are talking of using the same random number to encrypt another message m2. So somehow he has an access to m1 as well as the ciphertext that is corresponding to m1 and ciphertext of m2, but he is not aware regarding m2. With this situation, we'll try to say find out the possibility of getting so possibility of getting m2. So let us have how mathematically it is possible. Let us see. m1 c2 c1 raised to minus 1 mod p will be equal to m into m1 into m2 into alpha raised to r mod p bracket complete into m into alpha raised to r mod p raised to minus 1 mod p. This will be equal to sorry, this will be m1 not m. Please make a correction. That is now m2 into m1 into m1 inverse mod into alpha raised to r into alpha raised to minus r mod p. By solving this, I am going to get m2. This is how we need to obtain the value of m2. This is what is a weakness of Gamal, where we are talking of a known plain text attack on Gamal. Discuss regarding Gamal signatures. It's one of the application of Gamal. So Gamal techniques are used to sign a document. So in this case, like as usual, small a is a private key and pg alpha will be the public key of party A. To sign a message yum, A does the following things. The first one, what he will do is he computes the hash function hm of a given message. Then he chooses a random number A, which is in the range of p minus 1 to 1, and r is relatively prime to p minus 1, like what we have discussed in our Gamal technique. Okay. So then here A computes x is equal to g raised to r mod p, and then in the fourth step again he computes y is equal to h of the hash function of the message minus a into x, the x1 which was obtained over here, into r inverse mod p minus 1. So the signature, after doing all this calculation, the pair xy will be the signature. To verify the signature, the following check is performed, that is alpha raised to x into x raised to y mod p is equal to g raised to hm mod p. It will be verified for the same. Okay, these two are matches, then the signature is correct. Let us verify whether the correct signature will going to balance this equation or not. Let us start the verification by taking y is equal to h of m minus a of x r inverse mod p minus 1, then ry. I rewrite this equation as I take this inverse on this side, it becomes hm minus a of x mod p minus 1. let me correct this equation. It is ry h of m minus a of x plus k into p minus 1. I have rewritten, I have removed this mod and I have written this division equation over here where k is some integer, raising both sides to power of to the power of g and reducing p, we get reducing mod p, we get g of r y is equal to g of h m g of minus ax mod p, and simplifying this equation using Fermat's theorem, it is possible to show that alpha raised to x into x raised to y is equal to g raised to h m mod p. The last technique in this topic is Schuner's technique. Schuner's technique, which helps us to reduce the key size to from 2000 to 400 bits, 2000 bits to 4000 bits. So Schuner technique helps us to reduce the key size, the hashed output size to 400 bits. So without compromising on security. So this technique works as follows: select P, a large prime, and about size is somewhere around 1000 bits. Then select a Q, one more prime, smaller than P, say about 160 bits long, which divides P minus 1. Let G be the qth root of 1 mod P, that is G raised to Q is equal to 1 mod P. Let A be some integer range which is less than equal to 1 P minus Q minus 1, and it is private key. Let alpha is equal to G raised to A mod P, and it is my public key, and this is private. The public key after calculation of alpha is this, like P, Q and G, in this case P, Q, G, not alpha, then G raised to A mod P. Let R be the random number whose value is P minus Q minus 1. Then Schuner's signature is pair xy, which is obtained as follows: x is equal to h of m concatenated g raised to r mod p and y is equal to r plus ax mod q, and these two will be the signatures of Schuner technique. This completes the discrete logarithm chapter, and in the next class we will talk regarding key management. Thank you very much.